everyone, welcome back to History of Physics, Chapter 1.3. Last time, we covered the Islamic Golden Age. Today, we will follow that thread into medieval Europe, where two thinkers in Paris pick up right where it left off. It is 1300s, and we land at the University of Paris. Here, we meet Jean Buridan, a philosopher, a priest, and by most accounts, a genuinely sharp debater who picks up an old, half-finished idea and actually runs with it instead of just admiring it from a safe distance. Let's set a scene, because it matters. Buridan is working inside a university system that's still officially Aristotelian. Aristotle is the authority, and questioning him is a bit like correcting your professor in front of the class, except this professor died over 1,000 years earlier and still somehow wins the argument by default. The specific problem Buridan inherits is the same ones we have been circling since Ibn Sina. Why does a thrown object keep moving after it leaves your hand? Aristotle's answer that the air rushes around behind the object and pushes it forward is definitely the kind of explanation you give when you are improvising and hoping nobody checks your work. It had been quietly unconvincing for over 1,000 years. Ibn Sina had already proposed a fix with his idea of impressed force, something that object carries internally. Buridan doesn't just borrow that fix, he rebuilds it, term by term, into something sharper. He calls it impetus. Here's the core of it. When we throw something, we're not just launching it. We're loading it with an internal quantity that keeps it moving under its own power. No ongoing push required. That alone would be a solid contribution. But what makes Buridan genuinely important is that he goes one step further and asks what that quantity actually depends on. He proposes impetus scales with two different things would immediately recognize: how much matter the object contains and how fast we got it moving. Heavier object, faster throw, more impetus stored in it, and the longer it takes to dissipate and bring the object to rest. Sit with that for a second, because quantity of matter multiplied by speed is, in plain language, a rough sketch of momentum, a concept we actually hand entirely to Newton, arriving in Paris 300 years ahead of schedule, no invoice sent. We should be honest about what Buridan doesn't have though. He doesn't have algebra as we'd recognize it, and he certainly doesn't have calculus. His reasoning almost entirely inverts careful, logical, scholastic argument, and the kind of medieval university disputations were built on, not equations. So impetus isn't a formula we could plug numbers into. It's a concept argued into shape through logic rather than measured into shape through experiment. But conceptually, he's standing right on the top of one of the load-bearing pillars of classical mechanics, 3 centuries before Newton gets the credit. And Buridan doesn't stop at rocks and arrows, which is honestly the part of his history we find most delightful. He takes his own idea and points it straight at the heavens, because why solve one small problem when you can casually reframe the entire cosmos? He wonders, in writing, whether the planets might simply be bodies that received one single burst of impetus from God at the moment of creation, and have been coasting on that original push ever since, spinning and orbiting with no ongoing divine hand required to keep them moving. Think about it, what that quietly implies. If a planet can keep moving forever with no continuous intervention, then the universe doesn't need constant supernatural babysitting just to keep functioning. That's genuinely a bold thing to suggest out loud in 14th century Paris, inside a church-run university, no less. It's one of the earliest cracks in the old assumption that God has to keep actively pushing the cosmos along. From here, we follow Buridan's own student, Nicole Resmi. who takes the exact same underlying puzzle, motion, and how it changes over time, and comes at it from a completely different angle. Out of everyone we have covered in this whole series so far, this might be the most underrated contribution yet. Orithme's move isn't a new physical concept at all. It's something arguably even more foundational, a new way of seeing one. Before Orithme, if you wanted to describe how something's motion changed, you were stuck describing it in words, the way Buridan does. Orithme decides to draw it instead, which, in hindsight, is the kind of idea that sounds obvious only after someone else has already had it. It sets up a simple picture: time running along one line, speed along another at right angles, and he plots how an object's speed shifts as time passes. If a body speeds up at a steady, constant rate, what we now call uniform acceleration, the shape that emerges is a triangle. Simple as that. A straight line rising steadily from zero. But here's where Orithme does something remarkable, something that genuinely deserves more credit than it usually gets. He shows that the area underneath that triangle, the actual geometric space enclosed by that shape, represents the total distance the object traveled during that time. Register what that actually is, because it's ready to read past it so fast. That is quite literally a velocity time graph. The exact diagram still drawn on physics whiteboards in classrooms today, where the area under the curve gives you displacement. Orithme is doing this with a stick of chalk and pure geometric reasoning, roughly 300 years before calculus exists to formally explain why the trick actually works. He doesn't have integration. He has a triangle, some chalk dust, and a very good eye for what shapes can tell you. What is especially satisfying is how naturally these two ideas sit next to each other, even though Buridan and Orithme are doing genuinely different kinds of intellectual work. Buridan is sharpening the content of physics, taking a fuzzy philosophical pet job inherited from Ibn Sina and pushing it forward something almost measurable, even without the mathematical machinery to fully get there. Orithme is inventing the language of physics we'll eventually need to speak fluently. A visual, quantitative way of representing change itself, built entirely out of geometry, well before anyone has the algebra or calculus to justify why it's valid. And we can trace exactly where both threads lead. Buridan's impetus becomes a direct conceptual ancestor of Newton's first law, the idea that objects in motion stay in motion without needing a continuous cause to sustain them, which is, when we look at it, just impetus theory with the friction of quote-unquote it fades over time finally removed. Orithme's triangle becomes a direct ancestor of the graphs and eventually the calculus that Newton and Leibniz will need 3 centuries later to describe motion with real mathematical precision instead of sketching it by hand. Two medieval thinkers, a generation apart in the same city, quietly building both the concept and the visual language, a whole different scientific revolution will need later, neither of them sticking around long enough to see it pay off. And next time, we leave the philosophers and the bishops behind. We cross into the Renaissance, and we meet the man who points a telescope at the sky and picks a very serious fight with the Catholic Church over exactly what he sees there: Galileo. Thanks so much for watching video so far, and I will see you in the next video.